Prof. Yaman introduced me. I'm also director of the Sabancı University Integrated Manufacturing Center. So this is the picture of the center, and I will also briefly talk about that one as well. So, I mean, Professor Yaman actually took time to introduce me, but just briefly where I was in additive manufacturing, and also maybe help to some of you to see the journey where I was, and also see the journey how we move from rapid prototyping to additive manufacturing. I did my master's in 5-axis machining. So some of you might actually be in this area, I'm not sure. But after my master's degree, I was looking for a new topic for my PhD, and my advisor actually working in the 5-axis machining. So I said, like, there's a new technology, it's called the rapid prototyping at that time. And I was actually involved with one of the machine in the lab, and I make this is my first part in additive manufacturing or rapid prototyping at that time. This is the part, I'm not sure how many of you know, it's called the climb bottle, which is basically, I mean, you see the slice part, it's a infinite surface. It's a mathematical function where it's actually the surface is infinite. And after I see this one, I was kind of very excited about this area, and I said, like, okay, for my PhD I have to work on this area, and this is the first part that I actually printed, and I think this might be the second part, and this is still very impressive. I mean, you cannot make this part in any other manufacturing processes, so that's why I decided to do work on. So that was in 1997. During my PhD, I work on hybrid processes. I develop mainly computational algorithms for the hybrid processes. Hybrid process, I'm just using the master's degree knowledge or my experience in 5-axis machining and combining with additive manufacturing or adding material so that we can actually get the advantage of these two processes. And so that was in 2001. After I graduated, I moved to Buffalo, State University of New York at Buffalo. And at that time, in 2001, the economy wasn't good. Manufacturing wasn't really very popular. So I said, like, what can I do? Because I need to get funding. So I moved to biomedical applications, because in biomedical applications, there's still a lot of money. So I spent a lot of my time actually in 3D bioprinting. So when we add the bio to 3D printing, then we get the 3D bioprinting. I work on a lot in the 3D bioprinting. I got several grants from the Department of Defense and other NSF and NIH projects that I work with them. And so from 2001, 2010, I was at the University of Buffalo. And in 2010, I joined to Sabancı University. And I still work on biomedical applications or 3D printing or bioprinting of tissue and organs. And this is like one of my research area, very strong research area. And I have a big group in that one working on. But today I'm not going to talk about the biomedical applications. I will move more on the non-bio. And you see more aerospace or automotive industry related applications, and also related to what I actually work on in my time here at the Sabancı University Integrated Manufacturing Center. So I will talk about what we do at the center in terms of the additive manufacturing research, and how we move from rapid prototyping to additive manufacturing, where we can actually directly manufacture the parts which is actually part of a jet engine or part of an airplane or part of an automotive industry, cars. So that's what actually my journey. I'll talk about what we have done, what we working on at the center, and I will try to finish as quickly as possible because we have very limited time. So let me briefly talk about the center. Center is actually it's outside the university, which is actually in the Technopark Istanbul. The center was founded in 2016 with a 35 million US dollar coming from different sources, but mainly Sabancı University, Corsa, and Ministry of Development. So the idea was that can we have a center where we can work directly with the companies so that we can actually bridge the low-level technology readiness level, which is basically the fundamental research, to move more higher technology readiness level to from 4 to 7, 8, so that we can actually go more on the prototype or component production. So that center is actually fun, and it's one of the unique center actually is globally one of the best example for industry university collaboration centers. So the Corsa is one of the major partners in terms of the composite manufacturing, but we work with a TAI, Turkish Aerospace Engines, engine industries, I'm sorry. And also we work with other companies such as institutes such as TWI. I will talk about that one as well. So the center has several areas. Two areas that actually we focus on. One is the additive manufacturing. The other one is the composite manufacturing. And I'll talk about what we do in this one. We have total 12 faculty members directly working here, and also we have roughly 85 masters and PhD students, mostly PhD students. We have also hybrid structure. We have also technicians, engineers, and researchers directly working at the center. And that provides us that we can actually get, again, one of the unique thing about the center is that we can actually get certifications. Like we have one of the 6 university centers among all globally, which has this certification, which is the aerospace certification, one of the highest requirements in the aerospace, AS9100. And we also have the ISO 17025 certification. So that actually shows us that we are, the research that we do is actually directly can be certified and also can be applied to industry directly, depending on the project. Up to now, we have in 2 years 155 papers and also 16, it's not shown here, 16 patents. The overall budget of the center is 85 million US dollars actively right now working on projects, which is not including one of the largest project, the project budget that we receive, which is this is 85 million Turkish liras. We received another project recently, which is actually about 10 million euro that's related to additive manufacturing or digital manufacturing. These are some of the companies that we work, Boeing, Airbus, GE Aviation, TAI, Aselsan, Bombardier, Baykar, and so on and so forth. And I will skip some of those, but move to what we do in terms of additive manufacturing. If you're interested in to see the center website, you can actually go to SUIMC, Sabancı University Integrated Manufacturing Center at sabancı.edu, so you can get more information. Yeah, I'll skip to, because we have very limited time, I don't want to take a lot of time with the center, but focus more on what we do, part of my research, and also what we do at the center with other researchers. So besides me, we have several researchers actually working at the center related to additive manufacturing. So the research areas that we work on, and I will briefly mention some of them, but we don't have much time to go in detail, but if you have a question, I can answer. So we work on design for additive manufacturing. I will mention about some of those things. We work on the analysis, thermomechanical analysis. We have a faculty member working on, two actual faculty members working on this area. We work on the novel process development, new additive manufacturing processes, new materials, novel materials that is developed for the additive manufacturing. We have we work on secondary and surface finishing operations, and also we have very strong test and characterization laboratories for that one. So let me just briefly go through what we do for each of those areas. So in design for additive manufacturing, we have several projects that we finish. Also, we are working on some of the research areas. So one of the area that's actually design and optimization for additive manufacturing. So we have a new research project that's actually recently approved. We are working on topology optimization that you see one example here that actually combines the generative design. So I don't know, I mean, how much you know, but in topology optimization, we try to reduce the weight. But when you reduce the weight, if the structure is not suitable for additive manufacturing, or if it is not possible to manufacture, then there will be a problem. Also, you can optimize the structure, but when you actually print, there are a lot of thermal problems, like residual stresses, thermal deformations. So because of that, there are a lot of constraints, and also your objective is to reduce the weight. So right now we are working on to optimize the structure, which actually can reduce the weight. At the same time, under the constraints from the additive manufacturing, as well as the thermomechanical analysis to actually understand this material. So this is what we have worked on. We have some work that's actually accomplished, but we have a project that's actually still going on. Second thing that we work on is the design for lattice structures or hierarchical structures. So we actually, you see some of them here. So we actually optimize them based on some of the mechanical structures. We optimize them. So we developed our own code. I mean, there are several work that actually uses those readily available softwares, but here we actually go from meso level optimization to nano level optimization. So we model them. So here you see here that actually nano composites. So we can actually embed those fillers such as carbon nanotubes or carbon nanotubes with the spiral form. So we can embed them, we can model them based on the material homogenization theory. So we can model them. So this is the part of the material. And then from here, we can also optimize the meso scale and also micro meso scale structure. So at the end, we can have fully actually optimize based on the requirements. We can actually develop this optimum structure. So we can go from nano, meso, nano, micro to meso, and also macro scale modeling that actually we develop those algorithms. Another thing that we work on is the path planning or scanning or deposition. Path planning for like scanning for the selective laser melting, or deposition for the extrusion-based processes. So we can actually develop continuous process. So we can actually take the structures and then without really moving, we can actually create the whole structure. So this is one example. So this is a lattice structure. I'm not sure if you can follow, but this is 2 layers to just show the idea. So here we can actually start from one and we can make a zigzag fashion. And also later in the second layer, we can go into more spiral section. And you may not believe this one, but this is only the whole layers is actually almost totally completed. So it's like there is no stop and start. So we actually can generate this one. So this is actually related to multifunctional structures. So during the printing or during the actually extrusion process, we can change the material. So here you see that this blue and the green, this represents two different materials. That's actually internal features. And the red one is another material. So this, as you can see, we move from blue to red and green to red by gradually. So we can actually change the material functionality or structure functionality. So for example, I can go from soft to harder material, or we can go from thermally more conductive material to less conductive material. So I can actually combine this structure. So that actually brings up the older research that we work on, modeling of the heterogeneous structures. So we can actually model these structures, heterogeneous objects, or it's also called the functional gradient materials. We can change the material structure, such as in this one you see here, I can actually change the material function, and in this taking the, like a very simple geometry, by changing the material function, I can actually achieve different material composition. These are all continuous. For example, let's say red, saying that like this is thermally conductive material, green is more stronger material. So I can actually change the material composition as well. Okay, so this is like what we do in terms of modeling. So, and again, some of those things that I explained, some papers that we publish, like for example, nanocomposite structures that we embedded, and we also printed those structures, and then we show that like by increasing the concentration for just like a small amount, 0.5 carbon nanotubes, we can achieve much structure. So as you can see, from material to actually micro scale modeling, we can actually do. Again, I'm just going through very quickly, so if you have questions, I can answer more in this later. I talk about multifunctional structures here. So we also develop a new process where we can actually print with the different functionality. So here you see that this is the thermoset materials or hydrogels, where we can actually include the conductive materials inside. Also, we can change the stiffness. And this is fully continuous, so I don't have to. So as you can see, this is a conductive, non-conductive, and this is non-conductive, conductive, non-conductive. So I can directly print in one structures without actually using more than one nozzle. We extend this one, so we can actually hybrid additive manufacturing of multifunction structures. So for example, this is the part that we want to print. So these are showing different materials, different functionalities. And we have the, like this, you can think about as a composite structures. We have thermoplastic and thermoset materials, and these are the functionalities. So I can print the thermoplastic material first, and then I can print the thermoset materials. As you can see, this is one layer. I can control the whole structure. So I'm basically combining this method with the thermoplastic printing, so that I can actually achieve the different functionality. Again, these are all published in the journal. So if you have questions, I can answer, or you can go through these papers. Second thing that, again, we talk about the design for additive manufacturing, and also for thermomechanical modeling. So I'm not directly working here, but I'm collaborating with a faculty member at our center in the project that I mentioned, Topology Optimization for additive manufacturing. Here we have 3 faculty members directly working on the thermomechanical analysis. So basically, what we work on is thermal processes. So when you print, or when you actually use selective laser melting or DED, directed energy deposition, how the thermal process works. We use peridynamic. So this is again a novel idea that you see here, that we can model the structures with the peridynamic modeling, where we can also model the crack initiation if there is any residual stresses that actually forms, that actually causes the cracks. So we can actually model that one, again, using residual stresses and also using that for crack one. And as I told you in our project, we are working on to minimize the residual stresses, reduce the weight, and also avoid any cracks so that we can actually strengthen those areas. And at the end, we can make the part can be additively manufacturable in the processes. Okay, so we have topology optimization, as I mentioned, and also physics and microstructure-based analysis and optimization. Again, we develop our own algorithms, our software, so we are not using readily available or commercially available software, and there is also no commercially available software that can actually do this type of topology optimization with the modeling as well. For process development, I mean, we design, we analyze, we also develop new processes. So as I told you, for my PhD, I work on the hybrid processes. So we have a hybrid machine. And as I told you, I work in 1997, but this was commercialized in roughly 3 years ago, in 2017. So for hybrid processes, during my PhD, some of those algorithms actually was part of the Unigraphics, and also later Siemens actually purchased the Unigraphics. So it's part of that algorithms, actually part of that software. So we work on those software because of using the advantage of the hybrid process, so that you can use directed energy deposition to add metal and then use machining to get much better surface finish. So we work on this hybrid process for DED, directed energy deposition, as well as for the hybrid process. With the TEİ, Turkish Engine Industries, we work on electron beam melting. So new process development and also secondary surface finishing operation for electron beam melting. Again, this is a kind of secret project, so I cannot tell you much on details, but we work on electron beam melting. And we also work on robotic-based large-scale additive manufacturing. As I said, 2 areas the center focus on. One is the composite manufacturing, the other one is additive manufacturing. So this actually combines composite manufacturing, and also machining operations. So in the composite manufacturing, we develop a continuous fiber printing. So we can actually continuously print the fiber, but also we can use the chopped fiber, carbon fiber, so we can actually have the composite printing. The advantage, so this is the process that we develop. Advantage here is that we can go to very large scale with the robotic-based system. So this is the just the schematic of the cell that we develop. Here, each robot has a degrees of freedom, 60 degrees of freedom. This table can rotate, so it is 13. And this table also rotate and tilt, so 15. And we can control 15 degrees of freedom at the same time. Not only that, we can actually also get 3 meter by 3 meter size in this table, or 1 meter size in this table with the rotation. So this is again what we have worked on. As I told you, with the nanocomposite, we can actually print with the nanoscale reinforcement materials that we are working on. And recently also we are working on using the graphene as in the energy storage or supercapacitor. So we are working on one project. And as I told you about the composite materials. So this is like some of the papers that we published that you can actually achieve. For materials, we work on the standard materials. I mean, at the center in Inconels mainly, that because of the parts that we work on mainly for the aerospace industry, but we work with the 316, magnesium steel, aluminum, cobalt, chrome, titanium. Besides this one, as I said, we have other researchers. Actually, she's right now at the ODTÜ, but she's also working as a part-time here with some projects. Our faculty member actually working on the oxide dispersed metal alloys. So these are actually try to improve the thermal properties of the alloys. Normally, inconels actually are used for the hot part of the jet engine. With the ODS materials, we can actually achieve much higher temperature strength of the materials. And same thing with the high entropy metal alloys. That again, objective is to work on the high temperatures applications. We work on also printing of function graded material, as I mentioned, changing the material structures from like a direct energy deposition. We can actually, right now, for example, we are working on to change from copper to inconel. Again, these are, if you think about this, is like a total opposite structure materials, but we can actually change the from one part from fully copper to fully inconel, and this actually changes based on some functionality that I mentioned for designs. We can also develop thermoplastic thermoset materials, again, at the center, and nano-reinforced materials, again, carbon nanotubes, graphene, and other materials. With Özbolt from our university, we also work on the ceramic materials, oxides and aluminum oxide, and also iron oxide materials that you see here. At the center, we have the secondary processes. We can do machining, heat treatment, and blasting. Again, I will talk about another project that we actually extend this area. We have very strong in terms of the material characterization. We can do microstructure analysis, XRD, SEM, TEM that we have at the center and also at the university. We have a hardness, surface hardness test. We can do mechanical tests. At the center, we have one of the only machine, like in mechanical testing. I just want to show you in terms of scale. So for example, this machine can go 250 kilonewton for static test as well as the torsion. This is again only machine in Turkey that we have. So we have very strong mechanical testing, dynamic DIC, digital image correlation, dimensional tests such as CMM, laser, and optic. And recently with the project, we will also get in the CT scan as well. For additive manufacturing equipment, again, this is just currently right now we have with the new project, we will be getting more processes as well. So right now for the hybrid process, we have the DMG laser tech. We have the robotics base that I showed you before. For composite materials, we have Markforge. Again, this can be used for composite materials. Also, we have automated fiber placement, which is basically it's kind of additive. I would say 2.5D. It's not 3D because mainly you make a thin structures. This is actually also robotic based, so we can go 6 meter long parts with the robotic based system. We can actually additively manufacture the fiber placement of the composite materials. For the prototyping, so these are all industrial scale, but for prototyping, we have the Ultimaker Markforge, SLA system, Formlabs. Again, some of them are on campus, and also multi-jet modeling. Again, this is just the capacity that we have at the center, and some of them are on campus. As I told you, for design analysis, we have very also strong high performance computing. We have all kinds of software systems. We have HPC high performance computing servers. All the software that I think you can think about for additive manufacturing, we have the licenses. I just want to also mention about, we don't have much time. Recently, we received a project, and that was actually approved for about 10 million euro project. It's called a Direct Digital Manufacturing Platform. So in this platform, we try to actually uplift the companies in Turkey, especially using the additive manufacturing for digital transformation. For this project, we mainly focus on the certification and also secondary operations so that we can actually additive manufacture part, and that can actually put into a jet engine or can be used directly in the aerospace industry. So that so it will be just starting right now. We will be probably active in 2021 for this project. Again, this is a large scale, about 10 million euro project that was actually supported by the IPA EU project. These are some of the projects that we work on. Again, I think I'm out of time. I maybe excited past the time. But we have several TÜBİTAK projects, EU projects, CESER, the defense related projects. I have some biomedical application as well, that's projects as well. But as I said, again, very limited time, and I don't want to take a lot of time going through details. If you're interested, you can go to center web page. You can get more information, or you can send me an email. I will be happy to answer your question through email, or I will stop here and then answer your questions, since I think I will give you also more time to ask me a question, and I can maybe go through more details. Thank you. And this is the machine that is the hybrid process that you see. It's running directly live. That's actually making a popular. Just mention, I mean, this was a script project, but just want to show you like where we are in terms of the state of art with TEİ, Turkish Engine Industries. We develop one of the jet engine as a small, medium scale jet engine together. This was a kind of, a script project, but it was available on the YouTube. So I cannot tell you, but if you want, you can go find the jet engine. That is the TJ300. So if you search on the YouTube, you will see some more details. I cannot give you technical details, but I can say that with this project, we achieve 60% penetration or use 60% of the parts made using additive manufacturing. This is one of the greatest achievements, I think, globally. If you look at the other companies, I will not name them, but you can find out in all the presentation, the fuel nozzle, I mean, that we are like very happy to see our fuel nozzle that's actually printed, additively manufactured, is part of the engine, jet engine. But here I can say that we make 55 to 60% of the parts that's directly manufactured using additive manufacturing. And this was, in the first time, there was 2 prototypes, and it was the engine run without any problem. And still ongoing project, but as I said, normally I wouldn't tell, but still it is public. So if you want, you can actually look for, I cannot tell you give you the details here, but you can search online TJ300 engine, that you can get more details online. All right, so I'll stop here and then answer your question if you have anything.